Salutations. Let's go over the homework from 8.2, inverse Laplace transform. So the first one is that I assigned was number 5C, and that is, let me put this up here. We need the inverse Laplace transform of the following fraction: 5s plus 3 over s squared plus 1 s squared plus 4. Yeah, s squared plus 1 s squared plus 4. Okay, so now this is a trick. The one trick that I did not go over into the that's discussed in the textbook and didn't go over in the lecture video, so that's why I'm going to do it now. You can do the usual thing. So yeah, let's first see how should it look like. We know because it is factored, but both are quadratic irreducibles. So we each will contribute. So we know that this will be of the form we have an x squared plus 1 and a fraction where we have x squared plus 4. And on top, what we have a linear polynomial degree 1. In what? In the variable that is displayed, the variable that is squared. These are completed squares, right, always. Because we want it in that form. If it's not in that form, we have to put it in that form. And sorry, we do that one, that is in the other exercise, we'll do this. So what we do now, well, the squared part is the s, so we go with the variable is s here. So we write this as polynomials in s. Now there are 4 coefficients that has to be determined, and that is annoying, because when you do a little bit this kind of partial fractions, you realize how easy or hard it can be. The more roots you have, a root kind of immediately gives you one of the values or one of the constants. But we have 0 roots. That is just means we will not have any of the constants to us. So we will have a system of linear. If we really work this out, it would be 4 equations involving A, B, C, and D. And that is something you can actually only solve using methods from linear algebra, which I am not assuming that everybody knows. And plus it would still be quite a lot of work, even if you know how to do it. So let's not, that method is, let's say, out of reach, is too much work. Instead, we're going to say, well, I'm going to look at this fraction. I find the partial fraction of this fraction. Now, how is this fraction related to the other fraction, the original fraction? The numerator we just ignore for a moment, and we look. It has to do with the denominators. So you see that what I'm doing is replacing s squared by x. So replace s squared by x, and then to go back, I will do the opposite, right? And I will replace x by s squared. So this comes from an exchange, calling as, if you want, is a kind of substitution rule, but we ignore the top. That's something that we'll think about later. Okay, so now we need the partial fraction of this guy. So we do the partial fraction for this one. So the partial fraction, now that we can use Heaviside for this. Okay, so this, we know this is a x plus 1 plus b x plus 4, right? And Heaviside says that a, what do we do? Well, you just take your fraction, scratch out that one factor that a is on top of, and now plug in x equals minus 1, the value that makes this factor 0. And so what we get is 1 over minus 1 plus 4, so that is 1/3. And what is b? Well, the same thing. We take again that fraction. We now erase the factor that the other factor, the the b is on top of this x plus 4, so we get rid of this x plus 4, and we now evaluate at x plus 4 equals 0 at -4. Okay, so this was 1 over -4 plus 1, so that is -1/3. So what we have is that 1 over x plus 1 times x plus 4 is equal to 1/3 x plus 1 minus 1/3 x plus 4. And we go now back to our guy here by doing the substitution x is s squared. So this tells me that 1 over s squared plus 1 times s squared plus 4 is equal to 1/3 s squared plus 1 minus 1/3 s squared plus 4. Now, we are almost there. What we have is 5s plus 3. So we're going to multiply this with 5s plus 3. So I'll do this here. So I'm going to multiply it with 5s plus 3. And here the same. 5s plus 3 and 5s plus 3. Okay. So let's see what we get. That is 5/3 s over, yeah, so and now we split that sum. 5s plus 3 we split in 5/3 s squared plus 1 plus 1/3 of 3, that's 1 s squared plus 1. And we do the same with the other guy. This is minus 5/3 s squared plus 4. And then the other term is a minus. The 3 and 1/3 cancel. I get 1 over s squared plus 4. So if you follow, I expand this. Okay, this expanding this will be 5/3 s plus 1, and I then split it. Take each term separately, and do the same here with the other term. Okay, why do I do this? Because these guys here are come from sines and cosines. Oh, I forgot my s. I forgot to copy the s here. Right, there's an s here. This s. Quick reminder, right? The Laplace of cosine omega t is s over s squared plus omega squared, and that of sine omega t is omega over s squared plus omega squared. Okay, so what is omega here? Well, omega in the first case, so in this case omega is 1. Okay, so we get 5/3, and then this fraction here, let me circle it, this fraction is just the one that comes from cosine t. And same for the other one, but this one is now for the sine. Okay, so plus I say cosine, I say sine and I write cosine, sine t. Now be careful, here we have a different omega. Let me do another color here. This omega, this is square of omega, so omega is 2 here. Okay, so we have to take into account in this formula that what you actually use is, no, let me do this in black. I don't want to. What you actually use is divide both sides by omega. Sine omega t divided by omega is 1 over s squared plus omega. Okay, don't forget that extra omega there. So we get minus 5/3, 1 over omega, 1/2, times, oh no, this is the cosine, sorry, this is the cosine, there is no dividing. The cosine you don't have to divide, there is no omega. Sorry, that was, that's in the next step we're going to do this. So here we have just this s squared plus 5, that is cosine 2t. And then we have minus this omega, so minus 1/2 sine 2t. 2 is again the omega. Okay, and let's double checking. This is what it is, right? So this is number 5c. Give me a sec here. 5/3 cosine plus sine. Just want to make sure that I don't have any of my. I think everything is correct. Okay. All right, and then the other one that I wanted to do was 7b. So 7b was the inverse stress Laplace of 1 s minus 1 times s squared minus 2s plus 17. Yeah, so going back to the previous one, if you would not have it done this way, you would invest a lot of effort in finding A, B, C, and D, whereas this method gives you what A, B, and C is. But you might say, okay, are we now doing something completely different? No, here. This is, if you expand this gives you AS plus B, and this will give you CS plus D. So you actually find these coefficients just simply that way. But this only works when you have something where the denominator only is all the same squares, and all quadratically reducible. Otherwise, it doesn't even make sense to do this. Okay. Now, here, this is not even of that form, but this is quadratically reducible. You can check the discriminant here is negative. So first we need to do is when you have a quadratic irreducible that is not a complete square yet, we have to complete the square. So we're going to write s squared minus 2s plus 17. Well, it is, you take the two terms that have the variable in it and separate, let us be a little bit space because we're going to add something. Namely, what we're going to add, remember, you divide this by 2. This would give me negative 1. And then you add the square. So you square this thing. So this would be a plus 1 here. But of course, if you add a 1, you have to subtract 1. The whole thing has to stay in balance, right? You have to think of this as scales, and you put one more unit of weight on the right-hand side, you should have to take off something else, otherwise it's out of scale. Or you can put it on the other side. But okay, so what does this tell us? That we get, remember, this is now the center, s minus 1 squared plus 16. So the fraction that we are looking at is 1 over s minus 1 times s minus 1 squared plus 16. And we know that this can be written as a over s minus 1. That's just a linear factor, and only multiplicity 1, so we don't have to worry about that. And here, this will be a polynomial of degree 1 on top, but not in the variable s, but in the variable in which we have the bottom expanded. Sorry, let me write this here as a minus here before everybody gets confused what is this. S minus 1. So I'm going to write this as b s minus 1 plus c. Because I'm doing that for making my Laplace transform later on easy. My inverse Laplace. Okay, so what do we do here? Again, we have nothing else recourse than simplifying the denominators and then plugging in numbers or comparing coefficients. So we multiply everything with this common denominator s minus 1 times s minus 1 squared plus 16, s minus 1 times s minus 1 squared plus 16. All right, so what is cancelling? Of course, you have the whole thing cancels here. Here the s minus 1 cancels, and here this quadratic reducible cancels. So I get 1 is equal to a s minus 1 squared plus 16 plus b s minus 1 plus c. This whole thing between parentheses, because the whole thing has to be multiplied with s minus 1 squared plus 16. S is s minus 1, s minus 1, sorry. Right, this is what left. I see sometimes people write products where they're multiplying a sum with something else without putting the sum in between parentheses. They somehow remember that is what they're doing, because later on I noticed that they actually know what they're doing, but that's fine at the moment. Perhaps you know what you're doing. Well, I don't know what you're doing because somebody else reads it, but even you afterwards, and you would look at it again, you would say, why, how did I expand this? Right, so use parentheses whenever you can. Okay, so we plug in the root. Now we have a root. So we have the root, and the root is s is 1. Okay, let's do that. So we have 1 equals 16a plus, oh, that is 0, right? This whole thing is 0 here. Okay, 16a. Oh, that's good. So we know that a is 1 over 16. A is 1 over 16. But now the next thing we would plug in is the center of our quadratic irreducible, after completing the square. But that is s equals 1. I told you this can happen. I just want to give you this one example where this happens. Normally it doesn't happen, but it can happen. So we have to plug in something else. So the center is 1 is already used. I mean, you can plug it in, but what is going to happen? The same thing as what happens here. So nothing new can come from that. So we have to plug in something else. So for instance, I plug in s equal 0. That's always the obvious choice. So I get 1 is equal to a times 1 plus 16, that's 17, plus minus b plus c times minus 1, and that is equal to 1. Well, everything is 1 here, right? Okay. Oh, I had that already, sorry. Okay, so, but we know what a is, so that is 17 over 16 minus minus plus b minus c. Okay, so we see that, bring that to the other side, so this becomes minus 17 over 16, so minus 17 over 16, so they cancel out, plus 1, so this is minus 1 over 16. So minus 1 over 16 is equal to b minus c. That's only one equation. We know we have to plug in something more. Let's plug in s equals 2. Okay, then we get 1 is equal to 17a again, plus if I plug in 2, I get b plus c times, okay, times 1. Okay, so we get, and 17a, that is a was 1 over 16, 17 over 16 plus b plus c, so bring this to the other side and get minus 117, 1 minus 117 16, that is minus 1/16, right, sorry, minus 1 over 16, and that's equal to b plus c. So we have these two equations, we can add them, so let's add them to the c's will cancel. I get minus 116 plus minus 116, that is minus 1 over 8, minus 2 times 1 over 16 if you want, equals to b, so b equals minus 1 over 16. Okay, and if I plug this now in here, then I see actually that c is equal to 0. So this was what we're doing here, 7b. Just want to make sure that this is also 7b. Yep, I think so. Okay, so let's write up what we have. So our original function, let me take it here, let me copy it. So this original function that's the one here, right? Is this thing is a, which is minus 1 over 16, or was it 1 over 16? There's a. Where did my a go? Ah, here. A is 1 over 16, so I get 1 over 16 s minus 1 plus, and now what I get here is b, which is minus 1 over 16, s minus 1 over s minus 1 squared plus 1. And normally there would be also a c, but the c is 0 here, so we don't need to split anymore. So don't split this, because this is s minus 1. We are in the right-centered value. Why? Because now we know that this is a cosine. Okay? So let's start with this one first. The 1 over 16, that comes out. So we are taking the inverse Laplace of this. So we get 1 over 16. Now 1 over s, we know that 1 over s corresponds to 1, right? The degrees go down by 1. I should say it the other way. From the Laplace transform, the degrees go up, but go in the denominator, right? It's 1 higher degree in the denominator. So that is 1 over s, but what does the s minus 1 do? That is the shift. What is the shift? A is 1. Okay, that will be, in both cases, our shift will be 1. So it is 1 okay, so that means e to the t. Remember, the shifting is done, right? EAT, you multiply f, that is the result, is you replace the Laplace transform of f, little f, by changing s into s minus a. Okay, that is that one. And what is the other one? Minus 1 over 16. It's the one with the variable on top, that's the cosine. So we get cosine. Well, we again have e to the t. I could have figured it out, but let me write it. E to the t. And then we have cosine. What is omega here? So the only thing we need to know is omega. That is 1. So this is cosine t. Okay? So the solution... what was this? 2.7b. B, just double checking that 1 minus cosine 40. I copied something wrong. 16, right? That was my factorization here, and I copied 1 here. So this is a 16 here. So how does that change it? What does that change? The omega changes, right? So okay, so this omega, let me get this on a smaller. This omega is wrong, right? So this is wrong. Everything else is correct. It's the omega. What is omega? Omega is 4. Okay, so we get 4t here. And so you can make, so this is our inverse Laplace transform. You can make it a little bit neater by factor out e to the t over 16. You get 1 minus cosine 4t. That's a bit neater of writing it down, but again, it's not necessary to do that. Okay? So you see there's little details you have to, the main bulk of the work is doing the partial fraction, and I'll always ask you something, for instance, question number 6 I didn't assign because there you would have to deal with more system of equations with more than 2 variables. I will always restrict it to 2 variables. That is a method you can easily solve by substitution or elimination. Although you actually have seen in 1275, at least some of you might have seen a system of 3 equations, 3 unknowns, 3 equations of 3 unknowns, but I will not ask you to do that. So that's the bulk of the work. But once you have that, you have to then get it back into, you have to do the inverse Laplace transforms, okay? And that is a little bit tricky, right? There is 2 things. There's the shift, and then when quadratic is reducible, there is also the omega that plays a part. Okay. All right, so I will also do some review for the quiz that we will have on this shortly. Okay.